This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon, everyone. So, first, midterm test. I understand that many of you had issues. Now, this is a small sample, but I just am wondering, anyone here who didn't have any issues? Can you raise your hand? Anyone? So, everyone. So, if you had some issues with the test, can you please raise your hand? Alright, so, okay. So what's the extent of the sort of issue? It will be a few questions, can't download the figures. Is that a common story? Yeah?
Yes.
Alright. Okay, so just to give you an update, I mean, we're trying to figure out what's happened. So we basically tested things before the test, and midterm test was online, like a practice test. No one reported issues. We did give you instructions on what sort of browser you need to have. That was online, so it seems that that's not an issue. So we sent basically a query to LMS support to basically see what's happening. So obviously it's right? I just need to understand a little bit the sort of extent and the nature of the issue, and then we will rectify. You won't be unfairly marked. So you won't lose marks. You won't. I mean, we will do something that's appropriate given whatever information we find. So don't stress, don't panic. I got lots of angry emails this morning, and I mean, look, these things happen. With all the sort of due diligence, we just can't predict sometimes what sort of will happen. So give us just a bit of time. I'm still receiving angry messages. So just give us a little bit of time to understand what's happened. And then, I mean, if it takes too long, I might just make a decision and rectify the problem. I will need to understand also the nature, how many people were affected and in what way. So we need to do some statistics just to see everyone's tests. Jean has probably about 300 emails in her mailbox, so that's very difficult to respond. So please bear with us. I apologize again. I don't know whether it's sort of problem on a technical side or human error or something. We will in any case rectify it. So I know there's a bit of sort of it's a difficult situation because you prepared for it, you were ready for it, and then things didn't work as planned, and we'll just do our best to not treat you in any way unfairly. Okay? So that's that. So I am a bit distracted because of all this, because I was still talking to different people about this issue. So this has been going on from the morning. So we just want to now concentrate. Yep.
Do you think your reset? So retake. So redo the midterm. Is that possible?
So what I just said is I need to understand several things. First, what's the nature of the problem? What was the cause?
Yeah.
Right? Because when we were testing things worked. And we didn't receive any complaints about the practice test. Right? So for us, this was as big surprise as it was for you. So I don't understand what the issue was. That's the first thing. The second thing is I don't understand yet the extent of the process. So I need to basically do some statistics to see what's the best course of action. Right? But as I said, we would do our best. No one would be unfairly treated. Right? So what I want to is test not in hacking computers, figuring out university programming system, but on actual materials. So I will do my best to accommodate it. What the next steps would depend on what I find out. And because if people, for instance, are sort of on average, are just having problems with a few questions, one or two, it will be a different solution from if 80% of people had problems with 80% of questions. I have to understand a little bit about what's the extent of the damage. Yeah, so this is I'm in the damage control mode, and yeah, I apologize. I must say I've done this for a number of years, and this is the first time that I see this sort of extent to the problem. So I really don't. I know that the university is moving towards Canvas from LMS. I don't know what's happening. I just need to talk to some IT guys and see what's going on. Because we've done this for a number of years and never really had such an extent issues. Often actual issues were on the student side because we have these instructions. If you follow instructions, you should have problems. That was the sort of situation so far. So just give me a bit of time and then I envisage that some sort of repetition of a test to some extent in some form, shape or form will be necessary. If people are unable to answer or access 8 questions, I can't just kill the mark because it's 30% of the total test. If it's a single question, it's a different story, right? So I need to understand these things. And maybe we will do things, just like for everyone, same thing, or we will individually adapt things. I need to understand what's going on, right? So, yeah, sorry about that. And let's see whether whether I can concentrate on this. And actually, my daughter called me, panicking. She's applying for a fellowship. She's doing a PhD in Walter Eliza Institute. 5 minutes before this lecture, I was talking to my daughter, who was panicking about her fellowship application. So I'm totally distracted right now. Anyway, let's see how we go. This should be easy stuff, so we shouldn't struggle. All right, so what we want to do in this workshop, we want to look now at the design of controllers like PI controllers, and maybe also some compensators with more general structure. And we will use still root locus for this, and maybe some other methods, but we would concentrate on steady state errors, overshoots, rise time in this whole lecture, and design controllers. So here is a simple question. So you are asked to consider this plant. So it's a first order plant, so just there is one pole, no zeros. You are asked to consider step input. So R of S here is a step signal, right? And you are asked to design the closed loop system. So you are asked to design a controller here. So controller is not given. So that the controller achieves 5% steady state tracking error and rise time less than 1 second. So we are talking about step references, and we're talking about steady state tracking error, steady state tracking error of less than 5%, and rise time less than 1 second. So in this question, we will consider a proportional controller, P controller, integral controller, and PI controller that contains both P and I actions. And the question is split into several sub-questions, all right? So the first question is to consider a simple proportional control for this system. So the block diagram is the same, except that now controller here is just K, constant K, right? And you need to compute a gain that satisfies the rise time requirements. So rise time is less than 1 second, right? So, by the way, we didn't cover that in lectures, but that's why we mentioned it in tutorials. Rise time for first order systems is roughly 2.2 of the time constant. So I just want to remind you what the step response is for first order systems. I'll just use, this is Franklin Powell book. So impulse response of a first order system is given here, and step response is given here. So if you remember what the time constant is, so you have a maybe system which is Ts plus 1, right? T is the time constant. So in this case, the pole of the system is minus 1 over T, right? So T you can read out from this diagram. So if this is an impulse response of this system, then the tangent at 0 would intersect the real axis at the time constant, right? But if you think about the definition of rise time, definition of rise time is basically time needed to go from, let's say, 10% to 90% of the final sort of value. So in this case, you can see that the rise time defined in this way is much longer than the time constant. It's roughly 2.2, so we will work with that approximate formula. So if we go back to our question, well, the first question is, what is the steady state tracking error associated with this choice for this for the controller that satisfy this rise time, and compute a gain that achieves both the rise time and steady state tracking error specification of 5% relative error. So what we need to do here, we need to use this formula for rise time. So we need to first calculate the time constant for this closed loop, right? Then we need to translate the requirement on rise time into the constraint on the gain, controller gain. And then we need to also look at how steady state error depends on the gain. And we need to basically choose gain that satisfies both. So let's do that now. So the thing that we are dealing with here is given in this block diagram. The plant is given, right, by 1 over s plus 1, and the controller is just proportional controller. So we are also asked to consider step reference inputs, right? So this is the block diagram we are dealing with here. All right, so the first thing would be to find the transfer function for the closed loop. So basically the transfer function that relates y to r, because the time constant for that transfer function would determine response, step response of this system. So we use just the algebra of block diagrams, and you know y over r is the transfer function for this system. And that's basically k times the plant, right, divided by 1 plus k times the plant, right? So that's exactly this. So when you just cross multiply, you have the transfer function is k over s plus 1 plus k. So this step is taken from algebra block diagrams for feedback connection of these two guys. So what I did here is I took 1 plus k outside, everything in the denominator. Why am I doing this? Why do you think? I want to figure out what the time constant is. So 1 over 1 plus k is then the time constant, right? So now if I apply the step input, then the step response, you know, will behave according to this transfer function, right? Times the 1 over s. And then time constant in this transfer function would determine the rise time. So in other words, what I did, I rewrote everything in this way where t is now 1 over k plus 1, right? So t is 1 over k plus 1, and that's the time constant. We said that the rise time is related to time constant is 2.2 time constant is the rise time in this case. So we need to both consider the final value and, you know, the time constant or the steady state error. So let's just consider all of these. So the final value of the output with the step input is basically s times y of s. Obviously, we need to check stability. In this case, the system is stable. Why? Because k is positive. So k positive means that time constant is positive. So the pole is minus 1 over t, right? Since t is positive, then the pole is in the left half plane. So the system is stable. We can apply final value theorem. So we can find what y infinity is. And obviously, what's the steady state error? It's 1 minus that, right? The steady state error is exactly 1 minus this. So time constant is given by this, we just did that above, and then rise time is roughly 2.2 that. So from the condition on rise time, we want this guy, rise time, to be smaller than 1 second. So that should be satisfying this inequality. So 2 times 2 divided by 1 over plus k, that's exactly 2 times t, because t is 1 over k plus 1. And that should be smaller than 1, so from here we just get that the gain should be greater than 1.2 to satisfy the rise time constraint. Yeah? All right, so now we can also consider, so let me just zoom in a bit. Yeah, this is better. All right. So if we calculate the error, it's basically R of s minus y of s. We calculated y of s already. So this turns out to be this thing here. So it's basically 1 minus the transfer function times 1 over s. Since the system is stable, I can use basically that the steady state error is limit as time goes to infinity of e. But that's via the final value theorem. Limit as s goes to 0, SES. So when I just apply that formula to the E of s that I calculated above, I just get 1 divided by 1 plus k. So then the condition that we were given is that steady state error is less than 5%, which means it's, you know, smaller than 0.05, right? Because in the final value for reference is 1, right? So 5% of 1 is 0.05. And that gives us this extra condition, which says, well, all of this should be smaller than 0.05. This is the steady state error. So that gives you that k should be greater than 19. So obviously, for rise time, we got the condition that k should be greater than 1.2. For steady state error, k should be greater than 19. So if it's greater than 19, then we tick off both boxes. So we basically satisfy both conditions. Any questions? Okay, so let's consider, so far so good, so let's consider the next one. So the next part of the question, the same question is given here. It says, calculate the sensitivity function for the system. So it says, what's the sensitivity of the system to constant disturbance? Well, we didn't talk about this, but what this means is constant disturbance is really like a disturbance with frequency 0. So when I substitute 0 into s, the transfer function, so this is s of 0. That's what we mean by constant disturbance. Why is this important? You will see, well, let's think about it. Sensitivity function relates, you know, or output sensitivity, relates how output disturbance affects the output, right? So if the sensitivity is 0 for constant disturbances, that means that step disturbances would still produce 0 steady state error. So s at 0 being 0 is good, right? In other words, for tracking of constant disturbances. We will actually do this in much more detail when we do frequency domain things. Here I'm just saying evaluate it, but the meaning and the reasons for why we are evaluating it, these numbers, would become clearer when we present frequency domain methods. So we are also asked to evaluate sensitivity as at s equal to j. You would see that if you do that, this will give you, if you take the magnitude of s at evaluated time j, that gives you actually the amount of amplification that the system gives to any output disturbance at frequency 2 radians per second. So if I plug in steady state, if I plug in disturbance at 2 radians per second, and I wait for the transits to die out if the system is stable, then the system would oscillate at a different amplitude. Now the ratio between the amplitude of the output and input is exactly captured by this sensitivity evaluated at that frequency. Right? We will learn about this more in frequency domain methods, but here we are just asked, this is the sensitivity function by definition, and you are asked to evaluate it at 0 and at 2j. That's all, right? So sensitivity function by definition is basically 1 divided by 1 plus g times d, where g is the Planck transfer function, d is the controller transfer function. Planck transfer function in our case is 1 over s plus 1, and controller transfer function is k. So this is basically the formula for sensitivity. That's what we get for sensitivity for this closed loop system, right? If we evaluate sensitivity at 0, which that's actually sensitivity for constant disturbances, right? So that gives you 1 divided by 1 plus k. So what this tells you basically is that when you increase k, you will get that this s at 0 is reduced. And in other words, the effect of constant output disturbances would be reduced on the steady state error of the system. That's what it means. If you evaluate s at 2j, we just substitute, instead of s here, we just substitute 2j. Now you will see later on that this basically sensitivity evaluated at 2j would have to do with the following. So if I plug in the sinusoidal disturbance of frequency 2 radians per second, so this is my transfer function, right? And so this is disturbance, output disturbance, right? And I observe what the output is, right? Output for stable systems would eventually start oscillating again at 2 radians per second. But it might have a different amplitude from the input disturbance. So you can read out the, both the amplitude of the output signal and the phase. There may be phase shift, so this thing may be 0 at points where this is not 0. So there may be some shift, phase shift, and you can calculate both of the amplitudes and phase shift of the output from the amplitude and frequency of the input and the sensitivity here, right? So basically this sensitivity here would give you all the information you need to reconstruct the output in steady state for stable linear systems. That's why we are asked to just evaluate it at this frequency. As I said, we will come back to that later, but that basically completes this part of the question. Are there questions? No? Here's the second part. It says for a straight integral controller, meaning the control transfer function is now k over s, right? Compute gain k that achieves rise time less than 1 second, verify that the steady state tracking error is 0. So now we are not asked to achieve steady state error smaller than 5%. You can actually show that it will be 0 with integral control. That's what we expect. Integral control, steady state 0 for step references, right? So that's done in the next step. So what we are dealing with here now is the plant is still the same, the reference input is still the same, and we just change the controller, right? The controller is k over s. We can play with k. K is still a parameter that we can play with, right? So now I first find the closed loop transfer function in this case. So basically just using the algebra block diagram is the transfer function for the whole thing is on top we have Planck times controller transfer function divided by 1 plus controller times Planck transfer function, right? So that turns out in this case to be this. So this is the transfer function in this case. So what we can do now is, well, first we are asked to look at the rise time. Now, why I'm using now a different formula? Look, I'm saying now the rise time is 1 over 8 divided by omega n. Why is that? It's a second order system, yes. So for second order systems, we use a different formula, right? So those formulas you can find in books. Let's see whether Franklin and Powell, they should have it. Yeah, so if you open Franklin and Powell, there is that formula here. Rise time for second order system is this formula. So how do we read out omega n from this transfer function? square root of k. Why? Because I want to represent this transfer function as something like, I don't know, omega n square, s square plus 2 xi omega n s plus omega n square, right? So this transfer function really is in this form, right? So I can just read out. So I just look at this term here. That should be my omega n square, right? So, and then if omega n square is k, then k should be greater than this by using this formula, right? So it's straightforward, right? So that gives us the constraint on k. So the next question we were asked to do is just to verify that everything is, I mean, the steady state error is 0. Well, note that, so what is this transfer function in terms of sensitivities? Do you remember? Which of the transfer functions, which of the sensitivities is this transfer function? Sorry? Complementary sensitivity. So note that in this case, complementary sensitivity transfer function would be stable because for any positive k, all coefficients in this polynomial are positive. So since it's a second order polynomial, that's a necessary and sufficient condition for stability. So we are good in terms of stability. So, but then, what is the value of complementary sensitivity at 0? What is the value of the complementary sensitivity at 0? When s is 0? It's 1. 1. No matter what k is, it's 1. So, and what is the steady state error for stable systems? It's 1 minus t0. T is complementary. So since 1 minus 1 is 0. So we can do the steps as given here. So since final value theorem holds is the system is stable, you know, limit as t goes to infinity is the same as limit as s goes to 0 ses. We just write, so this thing here is 1 minus complementary sensitivity, right? So this s and this s cancel, right? And then I'm just looking at 1 minus complementary sensitivity, and I need to evaluate it at 0. So this is where, you know, this 1 minus complementary sensitivity evaluated at 0 gives you really the steady state error. So and it is 0, right? Steady state error in this case is 0. So again, we are confirming what we've learned. Integral control gives you steady state error 0. And then this is just, you know, for sensitivity, you know, use a different formula, right? So the formula for sensitivity is 1 divided on 1 plus control times Planck transfer function. So when you simplify everything, you get that this is the sensitivity. Note, and we said that in lectures, sensitivity transfer function plus complementary sensitivity is always equal to what? To 1. To 1, yes, to 1. So know that this is indeed 1 minus the complementary sensitivity. So, and then if we evaluate this sensitivity at 0, that we get 0. Now what does this mean? This means that if I hit my system with step output disturbance, that would still lead to 0 steady state error. The system, the closed loop system would reject any constant output disturbances. And this is what we learned also from lectures, and this is due to integral control, again. Right? But this is now, we are doing all these things in an example. Right? And then evaluating the same thing at 2j is given here. We just substitute s by 2j. Why we are doing this again, I explained already, but we will revisit this when we do frequency domain methods from next week. All right. Are there any questions for this part? The next part, the next question was, let's see, where am I? So now we want to consider proportional integral control. So this is the guy here. And it says here, choose t equal 1. Then there will be pole 0 cancellation of the compensator 0 and plant pole. Note that t equal 1 means that the pole and zeros that we are cancelling are both stable. So stable pole 0 cancellations we can do. That's sort of allowed. Don't do unstable pole 0 cancellation. So, and then using this choice of t, calculate gain k in order that closed loop system response has rise time less than 1 second. And then what is the steady state tracking error? Show that it is 0. And what's the sensitivity again at these 2 radians per second? So, and then in the end, you need to comment on all of these controllers. So what we are doing here is we are told to choose the time constant in the controller so that the controller can be written as s+1 divided by s. Then the controller would have 0 at -1, and that 0 at -1 would cancel with this pole in the plant at -1. That was given in the instructions in this question, right? So when we cancel these two guys, we just have that the, what we are left with is just k over s. So that's the, product of the plant and control transfer functions. So if we use now k over s to calculate complementary sensitivity, y of s over r of s, we get this, right? And again, note that what happened here is, although the controller has integral action and plant has one pole, because of the pole zero cancellation, we are dealing with a first order system. Because we canceled one pole and 0, so we are still back to the, we are back to the first order system. So we have to use this formula for rise time. It's 2.2 times the time constant. In this case, the time constant is 1 over k. The transfer function is given here, but I take k outside, and then I have k times 1 over k s plus 1. So now I can read out the time constant is 1 over k. Yeah. So if I use this formula here for rise time, I can get that k should be greater than 2.2. Okay. So the system is stable for all k positive and also for k greater than 2.2. And if we calculate again the steady state error, we will get, so note here, what is the complementary sensitivity evaluated for S0? It's again 1, right? We again have integral action, right? So in the closed loop. So again, when we calculate steady state error, because of that, we get that steady state error is 0, right? So again, we managed to get the rise time we want, and we also achieve steady state error 0. I mean, in this case, again, sensitivity of the transfer function at 0 is 0, and at 2j it's given by this, right? So now you are asked to comment on the differences, or what each of these controllers does, or how well do they perform. Obviously the integral and proportional integral controllers give you 0 steady state error, right? So that's a good thing, right? Whereas the proportional controller gives you some finite error, and the higher the gain, the smaller the error, right? So there's more sort of discussion of comparisons between these different guys. You can also look at, how much controller gain you need to achieve all these things. So in the third controller, PI controller, we needed gain 2.2 to achieve all the specifications. And in the previous cases, we needed, so for the second case, we needed gain larger than 3.24. And if you remember, in the very first case, we needed controller gain greater than 19. So when we use proportional controller, we need higher gain, k, than in PI and I control, right? Higher gain generally may cause problems in terms of robustness. Imagine that you have any input disturbance, then that input disturbance will be multiplied by the controller gain. The higher the gain, the more it would multiply the effects of the noise. Controller input disturbance, right? Are there any questions for this part? All right, so let's do the second question. So what you are given here is transfer function for this system. Let's see. What's the system? You're given here 2 mass system. So you have a large mass, and that mass can move, position of that mass is captured by this y. Y is the coordinate position of the large mass. And then that large mass is connected to a smaller mass, it's assumed that there's a spring and damper here, right? So typically the spring force is the proportional to the, how much we stretch or compress the spring via Hooke's law. And this viscous friction force would be proportional to the difference of velocities between this point and that point, right? So this would be proportional to the difference between, x dot and y dot. And the control input that you are using here is u, right? So this is a two-mass system, so you want to sort of use your force to move these masses in a particular way. This problem can arise in robotics in many sort of areas. And, you want to first, find a transfer function for this system. Well, the transfer function is already given to you from, first model principles. You can, Newton's laws of motion, you can find the transfer function in this form. So, and then it says here that a smaller mass is typically significantly smaller. So that we use this notation, small m is less than m. So this means much smaller than the big mass m. And it says here the specified for small criteria are that the rise time should be smaller than 0.1 second and overshoot less than 10%, right? So this is the transfer function, and then you are asked to do the following. First, it says approximate this g of s by assuming m roughly equal to 0. Assume also this m is 1, k is 1, b is 0.1, and then it says look at the proportional controller, and then proportional controller can be chosen to satisfy the design specifications. So to achieve. So the design specifications are rise time smaller than 0.1 second and overshoot smaller than 0.1, right? Or 10%, right, overshoot. So let's look at the transfer function here. So when I set m equal to 0, small m, so this term disappears, yeah? So then this term disappears, so I just have capital M times this, and this term disappears, so I just have capital M times k. But note that what I have then is this is gone, and then I have capital M times bs plus k, everything in bracket. So I can cancel whatever is there with this on top, and what I get is 1 over capital M s squared. So that's actually given to you in the question to use this choice, this simplification. So if you do that, so this is the transfer function that we start from. So for small m, close to 0, then we can rewrite, so this drops out, so this is 0, this is 0, and this is 0. So we can rewrite everything by, s squared capital M times bs plus k. So we can cancel that, which is what I described. We have 1 over m s squared, capital M s squared. We were told to use capital M equal 1. So what we end up with is a double integrator. Right. So what this question amounts to is to consider closed loop where we have a proportional controller and a double integrator. So if we plot the root locus for this guy, well, what is the root locus? This is the open loop transfer function. So open loop transfer function has 2 poles at the origin. There are no zeros. So both poles are here, right, at the origin. So, and then there are 2 asymptotes because there are no zeros, there are 2 poles, 2 asymptotes. So basically this is the root locus. One branch goes up, one goes down. So the root locus follows exactly the asymptotes. And what can we see for closed loop system? Well, we can never stabilize the closed loop system by changing k. So we will always have that the closed loop system is marginally stable, right, for any positive k. You can see this differently. So what is the transfer function for this system? So g of s is what? So k over s squared divided by 1 plus k over s squared. So that is k, and then I have s squared, right, plus k. So what are the eigenvalues, the poles of the system? They are plus minus j square root of k. So you can see from there immediately that that's what root locus already told you, right? The closed loop poles are always on the imaginary axis. And their their frequency, you know, is square root of k, right? So obviously the first question is answered. We cannot achieve the overshoot that we are asked to achieve, and we cannot achieve the rise time we're asked to achieve because the system is marginally stable. It's not even stable, right? So in order to talk about, you know, for overshoot rise time to be meaningful, we have to have that, you know, the poles of the closed loop should be strictly in the left half plane, right? So that answers the first question. Any questions so far? No, okay. So, yeah, one of the things, so obviously the first question is easy because we cannot stabilize the system, right? But we were asked to, you know, achieve certain overshoot and rise time. So in order to do this, we need to translate, I mean, when we can stabilize, we would like to place the poles of the closed loop in a certain region, right? So the overshoot would give us, you know, basically a condition like this. So overshoot smaller than 10% means overshoot is smaller than 0.1, which would give you damping greater than 0.6, which gives you this angle with imaginary axis. This is theta, should be, you know, at least 37 degrees. Where do we get these things from? If you open book by Franklin and Powell, here is a relationship for second order systems. This is a relationship between overshoot and damping. So this is for the transfer functions that are in this canonical second order form. So if I look at 10% overshoot, 10% is here, right? So I go all the way to the graph, I go down, I get 0.6. Yeah, and 0.6 is the damping, and damping is equal to arc sine of that angle in the complex plane, or it's arc sine. So yeah, of this angle here. And then also rise time should be smaller than 0.1 seconds. So again, from the formula for second order systems, we can calculate that omega n should be greater than 18. So we would need to take, you know, radius of this semicircle 18, and so this is 18 j, right? So then the poles of the closed loop should be somewhere in this region, because we need to satisfy both the overshoot and rise time requirements. So now the question is, obviously in the first case, just with proportional control, we couldn't move from imaginary axis. So root locus was completely on the imaginary axis. So now we are given two other choices, and the question actually says you can use MATLAB to plot root locus. So what we want to do, rather than going through steps of root locus plotting, I want to just show you root loci, and we discuss the design issues, how you actually design these compensators. So what I'll do now, I will go to the solutions. So the first, so let's just talk about the, yeah, this is the question. So note, so we solved the first question. So with the choices we were given, we were asked to investigate what proportional control can do, and we saw it can't even stabilize the system. So now you're asked, using PD compensator, so the transfer function of the controller is k times lambda s plus 1, and then it says show that k and lambda may be chosen to meet the specifications. So meeting specifications means that the root locus would eventually have branches that are in this area, shaded region, right? Where, you know, we satisfy both the overshoot and rise time conditions, right? So we need to choose, you know, now this lambda and k. Note, what would lambda affect in the closed loop system? So I will just now plot the plant is still 1 over s squared, right? the controller now, we were told, is k times lambda s plus 1. Yep. So we are given here controller that looks like this. So k and lambda we can choose. Plant has, you know, this transfer function. So now we need to plot the root locus. So what would lambda affect? It would affect the 0 of the open loop transfer function. So note the denominator of this closed loop is 1 plus k times, and I will have lambda s plus 1 divided by s squared. So we need to consider now how to choose lambda and how to choose k. Now this is an interesting question, because I always told you root locus, you can play with one parameter at a time. But what you can see here is, well, sometimes you can actually deal with two parameters. Why is that the case? Well, lambda here just affects the location of 0. So I can pick lambda to force root locus to look a particular way, and then plot root locus for how k changes. So you can actually sometimes play tricks like that. So with this structure, you know, we would say, well, so I already gave you here the equation that we need to use to plot the root locus. So by the way, if lambda is negative, is that a good choice? Why? What would be the root locus for lambda positive? Sorry, negative. Let's just play a bit with this. I have a few more minutes, so we have 1 plus k, and then lambda s plus 1 or s squared is equal 0. So suppose lambda is smaller than 0. What would be the 0 in this case? Well, if I plot everything in the complex plane, I still have two poles from the plant, right? So I have double pole at the origin, right? But because lambda is negative, 0 is here. What is the root locus now? Well, this belongs to the root locus, and this belongs to the root locus. So this is the root locus for this system if lambda is, negative. So this is not a good choice. We will never be able to stabilize for positive k, right? So what would be then? Sorry, this is the other way around. The branch goes to the 0. Sorry about that. So that's the root locus in this case. How about if lambda is positive, then the 0 is where? So I still have two poles at the origin, they don't move. But now 0, by the way, this is minus 1 over lambda. That's the 0. But lambda is negative, so this is positive number. Right? So minus 1 over lambda, when lambda is positive, is somewhere here. Now, but note, so what would be the root locus? Well, would this part of real line belong to root locus? Sorry. So there are two poles here from the plant and 1 0 here, right? We can pick where we locate this 0, where we push this 0, right? So what would the root locus look like this, in this case? So would this part of real line be part of the root locus? No, because there are two poles here. How about this part? That is the one, and that is the, sorry, again, I'm bad with errors today. So I know that eventually one branch would, converge to the 0, right? So that's what we know. We know also that two branches would come out of these poles, but they don't go along this real line. They have to do something else. They have to go somewhere else, right? I'm not sure where, but they have to go somewhere else. But note how many asymptotes I have. I have 1. There's 1 0 2 poles, right? 1 asymptote. So I also know that this negative real line would be an asymptote. But note, here I wrote this arrow going towards the 0. What does this mean? Well, that means that these two guys, two branches, will do something like this. You know, you can show actually that they never cross the imaginary axis, but they will meet somewhere here. And then one of them would go to infinity and one of them would go to 0. So now, look at this. You know, we have now two degrees of freedom. Note, since I can play with this 0 here, I can push this 0 so far that it ends up in the desired region. So if it ends up in the desired region, where all my specifications hold, then I know that these two branches would eventually end up somewhere here. They would meet somewhere here, maybe. You know, you can calculate where. And then one branch would go towards the 0, and one would go to infinity. So if we place the 0 strategically inside the region that we want, then we will tick off all the boxes for the design. We will push root locus inside the region we want. And this is exactly what was plotted in MATLAB. So this is the origin in the complex plane, 0, 0, right? And the 0 was placed at -10, right? And this is well inside the region we want. And then, you know, you can check, you know, when you press this sort of, this box here and this box here tell you what the gain is at that point, what is the pole, what is the damping, overshoot, etc. So we wanted to overshoot less than 10%. This point here satisfies the overshoot. It satisfies the pole is minus 19.4, but we wanted natural frequency to be larger than 18. So we are good, right? So we satisfy all the, but know that here we could play with the 0, right? So that's a very, very cool sort of design idea. All right, we can, so we are running out of time. You know, the last picture is given here. So again, you know, you just given a different compensator. So with this transfer function, and then again, you could play with different, you know, pole and 0 of the compensator. You get a different root locus, but then with all the degrees of freedom, you can again pick zeros and pole of the compensator, so that root locus ends up with branches inside the desired region. So you can check that. All right. Any questions? All right, thank you very much, and I will be back with some more information about the midterm as soon as I have some more information myself.
May I ask you a question?
Sure.
But I don't think this one have the solution of the mid test. I don't think this one have the solution. It is this one. But my worst.
So are you talking about midterm tests?
Yes. Yes.
Let's postpone this discussion because I still don't know.
Okay. What's going on?
That's right. So let's postpone this discussion until we finalize. I don't want to talk about solutions
I'm
now.
not discussing the answer to you. I just inform you that this might be not correct.
Can you report this to Jing?
To Jing,
Yes.
right? Because I simulated at the MATLAB later on. I cannot find it a matching answer for it.
Yeah, I would appreciate that.
I think that there's some mistake in there.
Please report it to us. But I don't want to discuss any midterm things at this stage. Yeah.
So there is some chance that the midterm text will be retake, right?
As I said, I don't want to be, you know, definitive about it.
Okay.
Because I just want to have more information before I make a decision.
Okay.
But it will be fair, and at the moment things don't look.
100% on final, easy.
Sorry?
Just put 100% on the final.
This guy didn't prepare well.
This is like a lottery, right? For some people. Yeah. Look, these things happen. I apologize, but these things happen.
I'm just wondering about the expedition in but you said that yesterday when I asked you about finding your Thank you very much.